Alright, we're moving into section 7.8, our last section for chapter 7. We're talking about improper integrals. So the process of improper integrals involves integrating areas that are defined infinitely. So this would involve a lot of functions that have asymptotes, either vertical or horizontal, right? So if I have, a function like this, and I want to know what is the area under this curve from, say 1 all the way off until infinity. Well, this area technically keeps going on forever. However, at a certain point, there are this function gets so small and so close to the x-axis that the amount of area being added here actually could be considered negligible, right? It might be so small that it's really not contributing anything else to this total. And that's what we need to determine. We need to determine first of all, how to find this area, and then determine if that area actually does produce a value, or if it is just infinitely large, if it just keeps growing and growing and growing forever. Okay? So, we have two types, so we're going to start off with type 1. If the integral from a to t of f of x dx exists for every number t greater than or equal to x, then the integral from a to infinity of f of x dx equals the limit as t approaches infinity of the integral from a to t of f of x dx, provided that this limit exists. Okay, so maybe you never thought you were going to see limits again. Well, here they are. So the idea is if we're integrating an infinite area, so from a up until infinity, so it just keeps going and going, the idea is we compute the integral using a finite value, so we use from a to the variable t. We figure out what that value is in terms of t, and then we can take the limit and see what happens as t goes off to infinity. Okay? Does it grow infinitely large? Does the value actually approach one specific number, and that would be our area? And those are the questions that we're asking here. And then for part B, we have the same kind of thing, but just on the negative side. So if the integral from t to b exists for every number t less than or equal to b, then the integral from negative infinity to b of f of x dx equals the limit as t approaches negative infinity, integral from t to b of f of x dx, provided this limit exists. Okay. If these limits exist, then these improper integrals are called convergent. And if the limits do not exist, they are divergent. This concept of convergent versus divergent is one we're going to be exploring throughout the rest of the course, particularly when we get to our last chapter, chapter 11. This topic will come up again, but basically, when we say the integrals are convergent, it just means that even though the area keeps going on forever, the amount that it's adding is so small that it actually approaches a specific number. Okay, so the area actually ends up being 5, because we're getting closer and closer to 5 as we grow infinitely large. However, if it keeps growing infinitely large, and there is no one value the area approaches, we say that it's divergent, because the value diverges. Okay? And then, part C, if both of those integrals exist, so from a to infinity and negative infinity to a, if they're both convergent, then the integral from negative infinity to infinity is just the integral from negative infinity to a plus the integral from a to infinity. Okay, so, and this goes back to a property we see in Calc 1, which is that you can split up an interval into different pieces. So we know that as long as this integral converges and this integral converges, that means they both approach finite values, then we can add them together to get the entire value, from negative infinity all the way up to infinity. So let's look at some examples. So determine if the integral from 1 to infinity of 1 over x dx is convergent or divergent. Okay, so we have integral from 1 to infinity of 1 over x dx. Okay, so this is going to give us the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. Okay, and then the limit is just going to tag along here on the outside until we're ready to use it. So we have the limit as t approaches infinity of the antiderivative of 1 over x is the natural log of the absolute value of x. And then this is being evaluated from 1 to t. So then do the evaluation. Again, we haven't taken the limit yet, so the limit's still here. Oops. We get ln of t minus ln of 1. Okay. Ln of 1 we know is 0. So this is limit as t approaches infinity of ln of t. So as t grows infinitely large, the value of ln of t is also going to grow infinitely large. Okay, so the limit is actually infinity. Okay, so in other words, this integral is divergent. Okay, because the area keeps growing and growing infinitely large. Okay. Let's try another one. Now we have a similar looking one. We have the integral from 1 to infinity of 1 over x squared dx. So let's set it up again the same way. So 1 to infinity, 1 over x squared dx. This is going to be the limit as t approaches infinity of integral from 1 to t, 1 over x squared dx. Okay, and don't forget to include this limit. It is important. Okay, so we've got the limit. Antiderivative of 1 over x squared is negative 1 over x. And this is evaluated from 1 to t. Okay, and now let's go ahead and evaluate. So we still have our limit. Now we have negative 1 over t minus negative 1 over 1. So that's just going to be a plus. So we get limit as t approaches infinity. I'm going to go ahead and switch the order, put the positive 1 in front of the negative 1. Just personal preference. 1 minus 1 over t. Okay. Now as t goes to infinity, 1 over t is going to be getting closer and closer to 0. Right? Because if the denominator of the fraction gets bigger, the entire value of the whole thing gets smaller. So this is going to be 1 minus 0. So the value of this integral is 1. Or in other words, we could say it converges to 1. Okay, so the exact area under this curve from 1 to infinity is actually 1. Okay, so it's an interesting concept, the fact that it is an infinitely large area, but if you let it go towards infinity, the area will give you 1. So let's look at this next one. This next one is a little more of a proof. So we've already seen two examples of 1 over x and 1 over x squared. It turns out this function, the 1 over x to the p, so 1 over x raised to a power where p is just going to be some value, some real number. So the question is, for what values of p is this integral convergent? Okay, so based on what we already know, So let me type this here. So we already know when p equals 1, it's divergent. So let's assume p is not equal to 1. Let me go in and just make that not equal. There we go. Okay. So we already know that it's not divergent when p is 1, because that would just be 1 over x, and that was 2 examples ago. We saw that it was divergent. So let's assume that p is not equal to 1, and then let's play around with this integral. So we have the integral from 1 to infinity of 1 over x to the p dx. So that's going to be the limit as t approaches infinity of the integral from 1 to t of 1 over x to the p dx. And actually, you know what we can do? So when taking the antiderivative of this, because we're leaving it in terms of p, I'm going to go ahead and just put this in a form that's going to be a little easier to read, because we're going to be undoing the power rule here. So this is the same thing as x to the negative p power. So when we take the antiderivative of it, we have limit as t approaches infinity. We're going to add 1 back to the power, so x to the negative p plus 1, and then divide by that same value, so negative p plus 1, and this is getting evaluated from 1 to t. Okay. So now, when we do this evaluation, so let me just do this off to the side here. We're going to get t to the negative p minus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. So we have a common factor here, so I'm going to pull that out, and I'm going to switch the order, so it becomes 1 over 1 minus p. So we have t to the negative p minus 1 minus 1 to the negative p minus 1. Okay, 1 to anything is just 1, and then I'm going to make this a positive power. Okay. Oh, I'm sorry, that should be a plus, shouldn't it? Yeah, so that should be plus 1. Sorry about that, go back and change those into pluses. Okay, so this one still holds, that's still 1 to any power is just 1. This one, I'm going to take the negative of it. Okay, so we have 1 over 1 minus p, 1 over t to the negative p plus 1, like that. Apply the negative to it, so we get 1 over t to the p minus 1, and then that whole thing minus 1. Okay, so this is what's going right there. Okay, so let me just fill that in. So 1 over 1 minus p times 1 over t to the p minus 1 minus 1. I'm going to go ahead and erase this work so we have some more room. Okay. So this is the formula that we're going to be utilizing, okay, to determine what values of p are going to make this convergent. So next up, let's look at some different values for p. So we're going to start if p is greater than 1. So we know p is not convergent if p equals 1, but what about if p is greater than 1? So if p is greater than 1, then if we subtract the 1 from both sides, p minus 1 is greater than 0. Right? So that statement is equivalent. Right? So if p is greater than 1, then p minus 1 is greater than 0. So, as t approaches infinity, that denominator value, t to the p minus 1, so p minus 1 is greater than 0, so that means this is going to increase in power, right? Because that's going to be positive. So this value is going to get bigger and bigger and bigger as t increases, okay? Because its power is also positive. So this is going to approach infinity. And since the denominator is approaching infinity, then 1 over that must approach 0. Because again, the property of fractions, right, where if the denominator goes to infinity, gets really, really large, then the entire thing is going to get really, really small and head towards 0. Okay. So, thus, the integral from 1 to infinity of 1 over x to the p dx if this heads to 0, then that leaves us with just negative 1 times 1 over 1 minus p. So multiply the negative in, that's just going to be 1 over p minus 1. If p is greater than 1. And this, because p is just a number, right? It's just some arbitrary number. So this is convergent. It does approach a specific value. So thus, convergent. Okay. So we know that it's divergent when p is 1. We now know that it's convergent when p is greater than 1. So what about the last case? What about if p is less than 1? So if p is less than 1, then p minus 1 is less than 0. And we're going to make a similar argument here that we did just a second ago. So, as t approaches infinity, as t gets infinitely large, if p minus 1 is negative, that means that t to the p minus 1 is going to head towards 0. Right? Really big number to a negative power, okay, that's going to head towards 0. So 1 over t to the p minus 1 is going to head towards infinity because of a similar rationale where if the denominator is getting really, really small, the entire value is getting really, really big. Okay? So, kind of the opposite argument of what we just had in the previous case. Okay? So that's going to be heading off towards infinity. So if this value is heading off towards infinity, okay, no matter what this value is, as t goes to infinity, this is going to keep growing and growing infinitely large. So we can say, thus, these values would be divergent. Okay, so in conclusion, the integral from 1 to infinity of 1 over x to the p dx for any real number p is divergent if p is greater than 1 and divergent if p is less than or equal to 1. Okay, and these are pretty common functions to deal with in terms of their convergence or divergence. Again, we'll be seeing them later on towards the end of the semester. So, but let's go ahead and look at another example. So evaluate the integral from negative infinity to 0 of x e to the x. So let's move away from those rational functions. So start us off here. We've got integral negative infinity to 0 of x e to the x dx. So let's set it up in terms of the limit. So limit as t approaches infinity, or excuse me, negative infinity, because we're coming at it from the left now, of t to 0 of x e to the x dx. Now to evaluate this, we have to use one of our techniques of integration. We're actually going to use integration by parts. Okay, so integration by parts. So we're going to let u be x, then du is dx, dv is going to be e to the x dx, so v is going to just be e to the x. So when we perform the integration by parts here, don't forget that that limit is still hanging out in front as t approaches negative infinity. Then we get u times v evaluated from t to 0 minus the integral from t to 0 of v du, so that's e to the x dx, which is something that we can integrate, okay, with relative ease because we know the antiderivative of e to the x. So we get limit as t approaches infinity. So we'll evaluate this first one, so that's going to be 0 times e to the 0, so that's just 0, minus t e to the t. So we just get negative t e to the t minus e to the x evaluated from t to 0. Okay, so we get negative t e to the t, and then minus e to the 0, which is 1, and then minus, but we would distribute that negative, so it actually becomes plus e to the t. Okay, and then let me go ahead and split this into pieces here that we can work with, so we don't have to take these all at once. So we get limit as t approaches infinity of negative t e to the t minus limit as t approaches negative infinity. Oh, I keep leaving out these negatives, don't I? Negative infinity of 1 plus limit as t approaches negative infinity of e to the t. Okay, so then I'm just going to do a little bit of side work down here. Just so we can see these limits. So we've got the first one, so limit as t approaches negative infinity of t e to the t. It doesn't matter whether it's positive or negative t e to the t. You could put negative if you want. But this one is growing infinitely large. And this one, this one appears to be growing towards 0. So this one, interestingly, is I'm tripping over my words, an indeterminate form. You remember from Calc 1 what we can do when we have indeterminate forms. for limits, and that is use L'Hopital's rule. But in order to use L'Hopital's rule, we have to put it into a rational function. We have to put it into a quotient. So we have limit as t approaches negative infinity. I'm just going to pull the negative all the way out of this, just so we don't have to worry about it in our work. So we get t, and then to make this a quotient, I'm going to actually give e a negative power so I can move it down to the bottom. Okay, so now this allows us to perform L'Hopital's rule. Take the derivative of the top and the bottom separately, we get 1 over negative e to the negative t. So we get negative limit as t approaches negative infinity. And now I can go ahead and move that back up, so this becomes negative e to the t. So essentially what L'Hopital's allowed us to do was get rid of that t, that numerator, that was giving us the indeterminate form, because now as t goes to negative infinity, e to the t, as t gets more and more negative, that's going to get closer and closer to 0, right? Because you basically have 1 over e to a really large number. Then that's going to get closer and closer to 0, so the value of that limit is 0. Okay, the second one, that one is very straightforward. So the first one was really the tough one. So, but that second one is 1 because it's just a constant. And then the limit of the third one, by a similar rationale to this one, this limit is also 0 because as t grows towards negative infinity, that function is going to get closer and closer to 0 because it'll be 1 over e to a really large number. So this gives us 0 minus 1 plus 0, which is just negative 1. Okay, so we get that the area under the curve from negative infinity up to 0 for x e to the x is negative 1, right? Which, if you remember, integration just means it's mostly under the curve, right? Or under the x-axis, I should say. Okay, that's how we get negative areas involved in integration. Okay. So that is improper integrals of type 1.